In this set of lecture notes, we're going to briefly discuss another kind of two-dimensional motion, which we're going to call circular motion. And then, just like with all the other motion that we've discussed up to now, we're going to stick to motion specifically without really defining reasons for it. And then once we progress to forces, we're going to kind of come back to this and make sure that we understand why motion happens. So let's start with circular motion. You may recall that when we talked about vectors, we said that if you have a velocity vector, an acceleration vector perpendicular to each other, the result of this is the change in direction without change in speed. So let me schematically draw that. Okay, so let me write that too. If velocity vector and acceleration vector are perpendicular to each other, the result is change in direction and change in speed is 0, right? So remember, v was a vector on top is velocity. V without the vector arrow on top is the magnitude of velocity, aka speed. So here's how it works. Think about acceleration as delta v over delta t, right? So that was the definition. So we can rewrite this as delta v equals a times delta t. Okay, so what I'm going to do is basically just add these vectors graphically. So I'll have v initial, okay, plus make this acceleration perpendicular, and I'm going to end up with something like this. Now this is actually hard to see that this velocity and acceleration vector that initial velocity and the final velocity have the same speed. So it's actually kind of goofy the way that the textbook has it drawn. Is not quite perpendicular. Oops. So mostly kind of like this. Okay, with angle theta here. Okay. And then this is delta v, where we're saying that v final vector is equal to v initial vector plus delta v vector, right? So that's how we define delta v to begin with, right? Delta v is v final minus v initial. Okay, so it's kind of hard to see that these two pictures actually represent the same thing. The reason being that you can't really add velocity and acceleration vector directly. So when we add vectors as vectors graphically or algebraically, we have to make sure that we're adding the same vectors. So I can conceptually say that acceleration vector perpendicular to velocity vector gives us a change in direction. But in terms of drawing, I'm actually not going to really draw acceleration. I'm going to draw the change in velocity vector. So if I do this enough, so I'll start with v initial, and I'm going to have this delta v. Okay, so here's my v final, or I'll just call this v1. And I add this delta v again, same delta v, right? Quite like this, but something like this. Here is my v2, and I'm just going to repeat this process. It's not an easy picture to draw. It just kind of keeps going out of whack here every time that I'm drawing this. But you can see how this motion, or this delta v, kind of curls back to itself if I repeat it a few times. So the result of that, if I allow this process to happen for enough time, the result of this is circular motion. So instead of drawing this really goofy picture that's difficult to draw, I'm actually just going to draw what circular motion looks like. So just as the name suggests, here is a circle. Okay, and I'm going to just indicate the direction of circle. It doesn't matter at this point in time if I want to call it clockwise or counterclockwise, whatever. The point is this is two-dimensional motion, right, in plane. Now recall that whenever we have one or two or three-dimensional motion, velocity vector is always tangent to the trajectory. So in this case, the trajectory is a circle, so velocity vector is tangent to the circle. So I'm just gonna pick a few points and draw velocity vector tangent to the circle. So the way I'm trying to draw these is in such a way that speed stays constant. So velocity obviously changes because direction changes, but speed is constant. I hope you guys remember that we refer to motion with constant speed as uniform motion. Okay, so in this case, as the entire path of the object is a circle, we're going to refer to this as uniform circular motion. Pretty self-explanatory. Uniform circular motion. Again, uniform means speed is constant. You will see a lot of times this kind of motion abbreviated as UCM. Now also remember that we said that this change in direction without change in speed happens when acceleration vector is perpendicular to the velocity vector. So let me draw acceleration vector at every point here, perpendicular to the velocity vector. And you will see that at every point, this acceleration vector points towards the center of the circle. This one's a little off here. Oops. Okay, so this acceleration vector always points towards the center of the circle. I'm going to label all of these as A with a subscript C. AC stands for centripetal acceleration. And the word centripetal literally means towards the center. Don't confuse this with centrifugal. The word centrifuge is probably familiar to you, so I'm not going to talk about it right now, but later down the line, after we have discussed forces, we're going to see what the difference between centripetal and centrifugal is. So centripetal acceleration. Sometimes you will also see it labeled as A with a subscript rad. This means radial. Okay, radial means along the radius of the circle. So basically represents the same thing, right? Towards the center, along the radius. There is an equation for it, which is a fairly simple equation. AC equals V squared over R. Now we are obviously always recycling letters, symbols. So R in this case is the radius of the circle. Okay, so I'm going to indicate it here. R is the radius. And V is the speed obviously, but a lot of times people refer to this as tangential speed. Sometimes people would even call it tangential velocity, but obviously we're not plugging in velocity into this because this is a scalar equation. This equation, the way that it's written, would make absolutely no sense as a vector equation, because remember, the most important thing of this is that tangential velocity is perpendicular to centripetal acceleration, right? So you cannot have, well, first of all, you cannot have a vector squared. It's a completely different mathematical operation, which we haven't done. So let's not worry about this. And second of all, if you're writing a vector equation, all the parts of it have to agree with each other. And I cannot say that my vector that points towards the center is in the same direction as vector that's tangent to the center. Tangent to the circle. So yeah, so that really makes no sense. So all of the quantities in this equation are scalar. And all the quantities in this equation are constant, right? So magnitude of centripetal acceleration, speed, and obviously radius are constant. So this is again the property of uniform circular motion. So we're not really doing much of anything else with this idea as of right now, but keep this in mind as we move on to talk about forces. So we'll talk about reasons for this motion, and then from there we're going to continue that discussion into discussion of more detailed circular motion, and then this will come into play again. So for now, this is all you need. You need to be able to draw velocity vector tangent to the circle. You need to be able to define centripetal acceleration and draw the vector perpendicular to the velocity vector. And you need to be able to calculate centripetal acceleration, which is a scalar calculation. And all of those quantities that go into that calculation are also scalars.